Hello everyone, and welcome back to Educator.com. I'm Dan Fullerton, and in this lesson we're going to talk about gravity and orbits. So, our objectives include determining the force that one spherically symmetric mass exerts upon another, determining the strength of the gravitational field at a specified point outside a spherically symmetric mass, describing the gravitational force inside and outside a uniform sphere, and calculating how the field at the surface depends upon the radius and the density of the sphere, stating Kepler's laws of planetary motion and using them to describe the motion of an object in orbit, and finally applying conservation of angular momentum to determine the velocity and radial distance at any point in that object's orbit. So let's start by taking a look at Newton's law of universal gravitation. The force of gravity, the force of attraction between any two objects with mass, is given by this formula, minus capital G, a constant, a fudge factor to make the units work out, times the mass of your first object, times the mass of your second object, divided by the square of the distance between their centers. And r hat, this means it's in the direction of r hat. So if we were to draw this, if we have object 1 and object 2 over here, and we define from 1 to 2 as the r vector, that means our unit vector in that direction, r hat, is that direction. So the force of 1 on 2 is going to be opposite the direction of r hat, so it's going to attract 2, force of 1 on 2. And that's where the negative sign comes in. Usually when we're dealing with this, we'll worry about magnitudes and use common sense to realize they're attracting each other. But the negative sign has to do with us defining the direction from 1 to 2 as in the r hat direction. Now, that fudge factor, capital G, the universal gravitational constant, that's equal to 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. And if we wanted to make a plot of the gravitational force between two objects as a function of the distance between their centers, we would have this inverse square law. Another place where as the distance increases between objects, we see the force go down as the square of the distance. So let's do a quick sample here. Find the magnitude of the gravitational force exerted on the Earth by the Sun, given the mass of the Earth, the mass of the Sun, and the distance between them. All right, well, let's start. The force of gravity is going to be minus G m1 m2 over r squared in the direction of r hat. But since I'm worried about the magnitude of that gravitational force is just going to be 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared, capital G, the universal gravitational constant, times our first mass, the mass of the Earth, about 6 times 10 to the 24 kilograms, times the mass of the Sun, about 2 times 10 to the 30th kilograms, divided by the square of the distance between them, 1.5 times 10 to the 11th meters squared. Put all that in my calculator and I come up with a force of about 3.5 times 10 to the 22nd newtons. All right, let's do another example. The diagram below represents two satellites of equal mass, A and B, in circular orbits around a planet. Compared to the magnitude of the gravitational force of attraction between A and the planet, the magnitude of the gravitational force of attraction between B and the planet is what? And you'll notice that B is twice as far from the center of the planet as A is. Well, because it's twice as far and we have this inverse square law relationship where the gravitational force is proportional to 1 over the square of the distance between the objects, if we double the distance, we get 1/4 the force. Answer C, because of that inverse square law relationship.